Most welcome to you all in my YouTube channel Learn Physics with a Clear Concept. Hope you are all alright. Previously we have discussed about Wheatstone bridge in current electricity. Today I shall discuss about meter bridge, wherein we have applied the principle of Wheatstone bridge. We can measure the value of an unknown resistance from the meter bridge. In order to clear our concept about the meter bridge, we have to see the diagram very carefully. In the diagram, it has been shown there are three thick metal strips are there, A, B and C. So A, B, C are three thick metal strips are there. That strips has been prepared from copper or brass. As these strips are thick and made so from the resistance of these strips are very negligible. So when we will calculate the resistance from the meter bridge, we will neglect the resistance of these strips. It has also been shown that there are two gaps in the meter bridge. One gap is in the left side, which is called left gap, and one gap is on the right side of the meter bridge, which is called the right gap. We have placed one known resistance R in the left gap. So we have placed one resistance R. The measurement of that R we have already known. So we have placed one known resistance R in the left gap. We have placed one resistance, unknown resistance S in the right gap. We have to calculate the value of this unknown resistance. So we have put it in the right gap. One meter long wire is there, which is connected between the A and C strips. One wire which is 1 meter long or 100 centimeter long, it has been connected between A and C strips. The cross-sectional area of the wire is same everywhere. The cross-sectional area of the wire is same, and this wire has been fitted between A and C directly. Now, one meter scale is there which has been fitted by the side of that wire, and from the meter scale we can calculate the distance, calculate the required distance from the meter scale. One galvanometer is there. The one portion of the galvanometer is connected in B, and the other side of the galvanometer has been fitted with a jockey, and that jockey we can move over the wire for the detection of null point or null condition of the galvanometer. So once again, one galvanometer is fitted between B and D, from which we can find out the null condition of the galvanometer. Now, one electric cell E has been connected between A and C points through a switch K. Now, if we switch on the electric circuit, then the electricity will flow from the higher potential towards lower potential. That means electricity will flow E to A and it will return back from C to E, which we have shown by arrow. So from arrow we can see the electricity will flow from higher potential towards lower potential. Now we will move the jockey over the wire. We will move the jockey over the wire, and suppose we have got one point, that means the point may be D, and at this point D, the null condition or balance condition of the galvanometer we have got. That means in that case no electricity will flow through galvanometer, and we can say that the potential of B and potential of D point is the equal, or we can say the potential difference between B and D uh, is equal to 0. So in the null condition of the galvanometer, no electricity will flow through the galvanometer. Now if we see very carefully this meter bridge, it is nothing but a Wheatstone bridge. It is nothing but a Wheatstone bridge. Let us see. We have studied Wheatstone bridge earlier. Here we can see A, B, C and D points are there, and we have fitted 4 resistance P, Q, R and S. Between the points B and D, one galvanometer has been fixed there, and between A and C we have fitted one electric cell through a key. If this is the null condition of the galvanometer, that means if the potential difference at the point B is equal to VB and potential difference at the point D is equal to VD, if VB and VD are the same, so in that case no electricity will flow through the galvanometer, and we can say that VB minus VD is equal to 0. So the potential difference between B and D will be the 0. So at the null condition of the galvanometer, no electricity will flow through the galvanometer. And previously we have calculated that in the null condition, in the balanced condition of the galvanometer, we can prove that P by Q, resistance P by resistance Q is equal to resistance R by resistance S. So P by Q is equal to R by S. This is the mathematical formula of Wheatstone bridge. Let us once again see the meter bridge. Here also A, B, C and D points are there. We have fitted one galvanometer between B and D, and we have connected one electric cell through key K between A and C point. So once again we have fitted one galvanometer between A and D points, and we have fitted one electric cell E through K between A and C. So it is nothing but a Wheatstone bridge. So from the Wheatstone bridge formula we can write R by S is equal to resistance of L1 by resistance of 100 minus L1. If we consider that the resistance of unit length of the wire is rho, then what will be the resistance of the wire L1? That will be L1 into rho. And what will be the resistance? 100 minus L1 into rho. That means 100 minus L1 into rho is the resistance of the wire 100 minus L. How it has come 100 minus L1? Because it is a wire of 1 meter, so we can say it is a 100 centimeter wire. So if between A and D the distance is L1, so the distance between D and C, it will be automatically comes 100 minus L. So the this portion, so the resistance of this portion will be L1 rho, and resistance between D and C will be 100 minus L1 into rho. So by applying Wheatstone bridge, we can write R by S is equal to L1 rho by 100 minus L1 into rho. Let us see. We have written here R by S. This is R, this is S. R by S is equal to rho L1. What is rho L1? This is rho L1 by 100 minus L1 into rho. 100 minus L1 into rho. So by applying Wheatstone bridge formula, we have got R by S is equal to rho L1 by 100 minus L1 into rho. So we can cut rho and rho. So what we will get, R by S is equal to L1 by 100 minus L1. So what we have to do? We have to calculate the value of unknown resistance S. We have to calculate the value of unknown resistance S. So from the formula, the value of S will come, S is equal to R into 100 minus L1, R into 100 minus L1 by L1. S is equal to R into 100 minus L1 by L1. So from this formula, we can calculate the unknown value of resistance S. So from the meter scale, we can get the value of L1, and from the meter bridge we can from the meter bridge we know that R we have used a known resistance, so we know the value of R, and we can measure the length L1 from the meter scale. So by applying this formula, we can determine the value of unknown resistance S. Now we'll now discuss about the sensitivity of the meter bridge. At what time the meter bridge will be very sensitive? It has been observed that if the null point is lying between 40 centimeter to 60 centimeters, if the null point we have detected between 40 centimeters and 60 centimeters, in that case the sensitivity of the meter bridge will be the maximum. It is not preferable to get the null point at 50 centimeter, that means exactly at the middle of the wire. So in that case, if we interchange the resistance R and S, if we interchange the resistance R and S, that means if we place S in the place of R1 and R we can place in place of S. So if we interchange these two resistance, then the null point will not be changed, it will be the same. So we can get, we could not calculate the average resistance in that case. Now what we have done from the meter bridge, we have calculated the unknown value of a resistance from the meter bridge by applying the theory of Wheatstone bridge. Now we can, besides that, we can also calculate the resistivity of a wire. We can calculate the resistivity of a wire. Now we will see how we will calculate the resistivity of a wire. Suppose we have taken a wire measuring L length and cross-sectional area is equal to A. So we have taken one wire of length L and cross-sectional area of A. So what we will get? The resistance of that wire will be proportional to length, directly proportional to length. L is equal to length, R proportional to L, and R is inversely proportional to the cross-sectional area of that wire. R is, that means R proportional to 1 by A. So from these two equation, we can get R proportional to L by A, R proportional to L, R proportional to 1 by A. So we got R proportional to L by A. So R is equal to rho into L by A. Here rho is a constant, and we can say it a resistivity of that wire. So what we got? R is equal to rho into L by A. In place of A, what we can write? Pi R square. We can write pi R square. If R is the radius of that wire, so A will be pi R square. So we can write like this also, rho into L by phi. In place of r, I have written d by 2 square. What is d? D is equal to the radii of that wire. So we'll get 4 rho L. 4, that means 2 square is equal to 4, and it will go to the upper side. So 4 rho L by pi into d square, where d is the radii of that wire. So finally, what will be the value of rho? Rho will come is equal to r pi d square by 4L. So we can get the value of resistivity from this formula. Here we know the value of R, because in meter bridge we have put one known resistance R. Pi, we know the value of pi. D we can measure by a screw gauge, the radii of the wire. The radii of the wire we can calculate by a screw gauge. And L, that L we can calculate, we can calculate the resistance, we can calculate the length of the wire. So by applying this formula, we can get the resistivity of a conductor. So today I want to stop here. Many thanks for listening my class. In my incoming class, I will discuss current electricity. I have to discuss so many items. So wish you best of luck. Thank you once again.